Hi, I'm Gašper. Occasionally I speak here. Most of you know me. So I've been at CitSec for about 9 years now, and I also wrote our internal sender-receiver implementation, so I should probably know what I'm talking about. So what's this all about? Like, that's really the only thing that I'm going to talk about in this lightning talk. Occasionally, this does not have my speaker notes. This is a problem. All right, improv. Okay, so occasionally we want to actually run our code. I don't know if you all know this. And so when you want to run your code, you give it to a thread and it does it. And the reason you do that is because the thread is what the OS gives you as an abstraction of a core, right? That's basically what happens. And if you want to run 2 bits of code in parallel or concurrently, you give them to 2 threads. And the tension that I'm talking about is that hardware is flat. It's just there. And we like composing our code hierarchically. We have functions that call other functions. We have classes that are composed of other structs, right? And fundamentally, there has to be a great flattening of function calling function into a flat instruction stream that the CPU executes, and then we have to put this hierarchical data somewhere, and that somewhere is usually called the stack, and the function's data is called activation frame. And that works for synchronous code like that, but for asynchronous code, have 60 years of trying to get this right, and we still haven't. So what happened with coroutines? Coroutines gave us language support for suspending functions and putting their activation frames somewhere else. Sometimes the heap, sometimes pre-allocated things, like they're very flexible. But it didn't give us language to talk about when and where these coroutines run. Stud execution gives us those concepts. It really just gives us our API, right? So it kind of says, okay, we have the flat world, we have the hierarchical world, and this is what we're going to call these things. The stuff that runs code, we're going to call execution resources. These are flat. They're just abstractions of hardware. And they all look the same. They don't have the same implementations, but they all look the same. They have scheduler, timed scheduler, and that's effectively what you get. We also have I/O resources, which also totally don't all look the same. But they need to have some idea of how they compose, and this is what stud execution calls domains. They're very useful. No way I can talk about them in this talk, so we're going to go on. So the structured bits get a bit more fun. So this is what a HTTP GET looks like in slide code. Sorry, slides. You connect. You have an async while loop if you want. That's an algorithm that I wrote. It's not standard. It's very useful. You can read next chunk, append. Once you're done, you're done. So let's try to do happy eyeballs, just for a fun experiment. The idea of happy eyeballs is you want your web page to load quickly, so you send the same request to several different backends, whichever one answers first. You display, you cancel the other ones to hopefully save load, right? This is kind of what that should look like. This is you have a when any, you send the 3 requests, and then the HTTP GET on the right is the same one as we just saw, right? However, what if we wanted to page through a bunch of things, and everybody in this room who has ever done crypto, this is what happens, right? Like you have to page through all of your stuff, and then that's a whole thing. And anyway, this is now a 3-layer asynchronous algorithm, which is absolute hell to write without a nice little structured bit of way to express it. But stud execution gives us that, which is really nice. I did say that when any cancels the rest of the requests, which is where the devil is. So the fun thing here is that obviously when any needs to say, okay, I can cancel things, and so all pages doesn't know how to cancel itself. Like it has nothing to do with cancels. It just needs to propagate all the information to the thing that actually does I/O, which is read next chunk. Now, read next chunk needs to know what the hell to do with the cancellation signal, but nothing else does. And yet we don't pay for this cancellation propagation with visual noise. And that's kind of the whole point. You can't forget to pipe your cancellation stuff because the library just does it for you. Now, if you're writing the library, then you need to do it, and it's a lot of fun. But we don't expect everybody to care about that. We only expect the people who write the library to care about that. And so you kind of concentrate expertise where it needs to be. And this is another really powerful feature of stud execution. We also have some verbs to talk about where exactly things run now, with the on algorithm, for instance. And we can just say, well, you know, run the first one on thread 1, and the second one on thread 2, and the third one on thread 3, and you pin those threads, and you know they're going to run lightning fast over HTTP. Just exactly what you want. The fun thing here is that it's really efficient, and you should absolutely look at Ben Dean's talk from C++ Now a few years ago, where he describes how Intel runs their little chiplets around the CPU, like the stuff that boots your CPU, that's also a bunch of chips, and they just run sender receiver on pure interrupts. It's lovely. We also can have concurrency without threads. In this case, we just have one thread, the main thread, and we use the sync wait primitive that gives the algorithm that it wraps the thread that started it to just do its stuff and wait. And because it's sync wait, it waits for it to complete, which means the thread is available for these things to actually use it and do their stuff. This is actually how our software a lot of the time runs internally. And it's, again, lovely, because you don't even need a mutex. It's all cooperative multitasking. So thinking differently about concurrency, this is structured, which means no deadlocks and no race conditions. All of this stuff, and by the way, all the algorithms I showed today on slides are in my library completely wait-free, which is great. No mutexes even in the implementation, because the structure gives you the ability to just not need them. Debuggers can deal with it really well. Why? Because all of the stuff is co-located and it's just structs. And Ian Peterson and Jessica Wong have a great talk on exactly one little bit that they needed to add to make debuggers totally understand this. So yeah, it's efficient. It's got clean separation of how from what, structured lifetimes, what's not to love. For closing, I want to say there's a really good anecdote. When I was writing a really particularly nasty piece of asynchronous reconciliation code, I realized that I literally don't know how to do it. I just didn't know how to do it. And so I wrote a whole C++ 17 compliant sender-receiver implementation from scratch, because there was none open source that I could use, because they're all C++ 20 plus. And then it was easy to write the component. So that actually worked out really well. I would encourage you all to give this API a really good look. What we standardized in 26 is like nowhere near enough, by the way. It's just we standardized the nouns and the verbs, but really nothing else. Like the pieces are not there. You need to use an external library, and the idea is that vendors provide you their little wrappers for their I/O devices and all of those kinds of things. So this is really a thing that brings a lot of different libraries together. It's not like the standard library is just going to give you all the implementations. But it's also not like BLAS where you link one and that's the holy one. This is like heterogeneity at scale. So that's what it's about. Thank you.